Okay, so now let's classify our couplings. And as we've just discussed, we're just going to use dimensional analysis. So let's put down what we're going to need to use. Okay, so the action. Oh, so as Amy Winehouse would say, let's go back to black. Um, so you know that the action is an integral d4x of the Lagrangian density. You also know that the action has the dimensions of h bar. So I hope you've all checked that. You should have checked that. We've used that a lot. And this is length to the naught, dimensionless in the units that we're using. And so the term that we usually use to figure out what the dimension of the field is just the kinetic term. So if we just think about the free field kinetic term, this would be an integral d4x 1/2 d mu phi d mu phi. Okay, so this is what we're going to look at to figure out what are the dimensions of the field. So if we think about the d4x, well, this is a dt, dx, dy, dz. And because we've set the speed of light to 1, we're measuring time and space as lengths. So this is a length to the 4. Then d mu itself, well, you want the dimensions of d mu. If you're looking at the dimensions of d by dx mu, so this is obviously length to the -1. So here we have a length to the -1. Here we have a length to the -1. So because we want the action to be dimensionless, what have we got? We've got length to the 4 times length to the -1 times length to the -1, and we've got a phi and a phi. So it's quite clear that we need both of these to contribute also length to the -1. Then we've got 4 lengths to the -1s, 1 length to the 4. So let's summarize that. We know that phi will also be a length to the -1. And actually, this is the integral d4x times the Lagrangian density. So we can also conclude that the Lagrangian density should be length to the -4 to give us an action that is dimensionless. So the only stuff that we're going to be using is what sits inside this black square over here. And now let's look at the different terms in our Lagrangian density that we've written down here, and let's try to see what dimensions they have. So the first term is this g to the n phi to the n. So we've got the dimensions of g to the n phi to the n. Well, this is a term in the Lagrangian density. So we know what we want this to be. We want this to be length to the -4. And we also know that this would be the dimensions of gn times by the dimensions of phi to the n. And phi is length to the -1, so that will just be length to the -n. So it's quite easy to see that gn has to have dimension of L to the n-4. So when n is equal to 1, 2, or 3, then gn is length to a negative number. And from what we just said a moment ago, this means that these parameters are relevant. So we've got here 3 relevant parameters. Then, if n is equal to 4, g4 will be length to the naught. And this we know, it's dimensionless, we know that this is marginal. And then finally, if n is greater than or equal to 5, then we know that gn, now n will be 5 or greater. So it will be L to a positive number. So this is just like our area, which was an L squared. And we know in this case, this is irrelevant. Now, look at this beautiful result. So if we look at this Lagrangian, we had an infinite number of these GNs, and what we've just argued is we only need to keep 4 of them. Why? Because these we drop. We drop the irrelevant terms. We only keep the relevant and the marginal. So we only have to keep a total of 4 terms. Good. I hope you can see what I did. It's a completely trivial exercise. I just did dimensional analysis on the first term sitting there. So now I want you to do dimensional analysis and figure out what are the dimensions of Cm. And once you've got the dimensions of those constants Cm, write down which are the ones that are relevant, which are marginal, and which are irrelevant. Okay? Pause the video and do that exercise now. Good. Did you do the exercise? So let's discuss it. This is what I got. So check that you got the same result. So when I did dimensional analysis on Cm, I found that this was length to the m. So what I found was, if you look at C naught, this is marginal. So we need to keep C naught. But then what I found, Cn with n greater than or equal to 1. All of these have a positive length dimension, so all of these are irrelevant. So in fact, there's only one constant I need to keep from here, and that's C naught. I throw everything else away. Finally, let's look at this term with the d's. So do exactly the same thing. Work out what is the dimensions of d to the p, just as we've been doing it so far, and then decide what relevant, irrelevant, and marginal operators there are. So pause the video, do the exercise, and then we'll discuss it. Good. Have you got an answer? So this is what I found. So when working out what are the dimensions of dp, I found that this was length to the 4 plus p. So actually, dp for p greater than or equal to naught is always irrelevant. So now I'm going to invite you to do something. So here I wrote down a lot of very general terms inside the Lagrangian density. Think of any terms that you can write down that are consistent with Lorentz invariance. Because if you remember, that was the only thing that's restricting the form of the terms that we write. And my claim is whatever else you write down, you will not be able to think of one more term that is either relevant or marginal. We've got all relevant and marginal terms. So we started off and just imposing Lorentz invariance, we found that there were an infinite number of parameters that this theory had. But now going to low energy and keeping only those constants that don't go to 0 at low energy. So dropping all of the irrelevant couplings, this is the form of the Lagrangian. We've got a term linear in phi. We've got a term quadratic in phi. We've got a term cubic in phi. So those are the only terms that were relevant. And then as far as marginal terms go, we had a term that was phi to the 4, and we also had a C naught over 2 and a d mu phi, d mu phi. What a remarkable result. So we started with a theory, a microscopic theory, the most general microscopic theory that we could think of. It had an infinite number of parameters, and by the time that we flowed to low energy, we found that our theory has a total of 5 parameters. That's incredible. Now, the way that I've written it, of course, the G's should naturally be negative because they would be part of the potential, but there would be some coefficient. I'm being completely agnostic about whether G is positive or negative. All that I care about is how large are these couplings and how do they grow or decrease as we go to low energies. And what we find is the result that's shown at the bottom of the page, that at low energies, this theory has a total of 5 undetermined parameters, regardless of what theory you started off in the ultraviolet. Of course, this is all assuming that we're at weak coupling, so that the dominant effect in the RG flow is just given by dimensional analysis. But what a beautiful result. We'll continue in a moment.